Hi everyone. Before we start, please let me tell you that I have created a Microsoft Teams group for this class, and we are going to have a meeting this week. Okay, so we have two lectures left on this unit. We are going to be talking about Pushdown Automata both today and on Wednesday. And on Friday, we are having a meeting, a virtual meeting through Microsoft Teams unit. And also, if we have some time left, I'm planning to solve some exercises from previous year's exams, okay? Similar to what we did at the end of Unit 1, okay? So you should have received by now an invitation to this meeting on Friday at 11 a.m., the usual time of our lectures. If not, please urgently send me an email to see what's happening. Okay, you should be able to see this invitation to log into Microsoft Teams with your Uniobi account and check all the announcements there. Okay, so please tell me if you are unable to see this invitation or the group or something. Okay, so I can fix it. Okay, so let's start this last part of Unit 2 with the study of what we call pushdown automata. So you may have noticed that so far in this unit we have only talked about grammars as a way of describing context-free languages, while in Unit 1 we had both regular expressions and finite automata. Okay, so in this unit we have mainly focused on the use of grammars because in practice they are more interesting and more useful than the automata that are able to recognize context-free languages, but there are also automata machines that are able to recognize these languages. And remember that from the very beginning we have said that we are interested in two ways of studying languages. One, which is what we do with grammars and regular expressions in order to describe the different rules of the language, which are the words that are in the language, which are the words that are not in the language. But we also are interested in the checking whether a given word is in the language or not. We have studied an algorithm, CYK, which is able to perform this task from a context-free grammar, but we would like also to study automata machines that are able to check whether a given word is in a context-free language or not, because they are equivalent to context-free grammars, and also because they are like an intermediate step between the finite automata that we studied in lesson in Unit 1 and the Turing machines that you will study in computability theory in your second year. Okay, so this is an interesting kind of machine because somehow it stays in the middle between finite automata and Turing machines. Okay, so the first thing to notice is that finite automata, as we studied them in the first unit, are not enough to recognize all the context-free languages that we are using for our syntactical analysis. So for instance, if we study the language of words with zeros and ones in which all the zeros are at the beginning, all the ones are at the end, and the number of zeros and ones is the same, we already know that this is not possible to be recognized with a finite automata. Okay, and the idea is that if we try to do something like this automaton here, we need to include an infinite number of states because we can read 1 0, then another 0, another 0, another 0. We don't know how many zeros we are going to read. And of course, when we read just 1 0, we need to read 1 1 in order to accept the word. But if we read 2 zeros, then we need to read 2 ones in order to accept the word. And if we read 3 zeros, we need to read 3 ones in order to accept the word, and so on. Okay, so this is not a formal proof of the impossibility of recognizing this language with a finite automaton, but the idea is clear enough. Okay, so the problem is that we only have a finite number of states, and the number of different possibilities that we may encounter are infinite. Okay, so we can find just 1 0 at the beginning, or 2 zeros, or 3 zeros, and so on. And each of these different possibilities must lead to a different behavior when we read than the ones. If we read 0 and then 1 1, we need to accept. But if we read 2 zeros and then just 1 1, we need to reject. Okay, so we must treat all these different possibilities differently, and the only way in which we can do that with a finite automaton is by having a different state for that situation. But we only have a finite number of states, and the number of possibilities is infinite. Okay, so what we need is something that can deal with this unbounded length of the string. Okay, because we cannot have an infinite number of states in a finite automata. So the idea is to try to fix this problem, try to extend the power of finite automaton, of a finite automaton, by including some kind of unbounded memory in order to be able to make a different treatment of all these different possibilities. And the simplest kind of storage that we can use in order to recognize context-free languages is what we call a stack. You may know about stacks from your programming courses. You know that stack is a memory in which we can store elements, we can push elements into the stack, and then we can recover, extract elements from the stack, but just in the order which is opposite of the order in which we included the elements. Okay, so for this reason, sometimes we call this type of storage, these memories, life, which means last in, first out. So the last element that we store in the stack is the first one that we can extract from the stack. This is similar to a stack of books or a stack of plates, in which we need to remove the books or the plates that are at the top before we are able to reach the ones that are at the bottom. Okay, so if we have something like this, a stack is sometimes represented like this. If we stored elements here, A, then B, then C, when we try to extract the elements of this stack, we first get C, then we get B, and then we get A. So we get the elements exactly in the opposite of order of what we used to include them in the stack. Okay, so this is the type of memory, the type of storage that we are going to use in order to be able to recognize context-free languages with automata. Okay, so the informal description, we always start with an informal description of the machine, is similar to the informal description of finite automata in Unit 1. So we have some elements that we already know, some elements that we are already familiar with, like an input tape, where the the string, the word that we are studying is written, we also have a unit, control unit, which is a finite state machine, so it can be in one of a finite number of different states. And we also have this new element, which is the stack. Okay, so here you can see in this figure here, in this picture here, that we have the input tape, we have the control unit, which is reading one of the cells in the input tape, and it always moves to the right, exactly as in finite automata. But this control unit also can access this stack and can manipulate, can change the information in the stack. It can add elements to the stack, what we call push elements into the stack, or it can recover elements from the stack, what we call pop elements from the stack. And we always pop elements from the very top. We always recover the element which is at the top of the stack. Okay, so this is similar to a finite automaton. We have an input tape with different symbols written in each of the cells, and we move to the right, reading the symbols in the tape. We change the state of the control unit, but we also change the elements that are in the stack. That is the difference with finite automata. And the information that we have in the stack can also influence, can also make the machine do different things. Okay, so the machine will take into account not only what it is reading in the input tape, but also what is stored in the stack. Okay, so that's the informal description, the intuitive idea of how a machine of this kind works. Okay, so this push-down automata will be the kind of machines that are able to recognize the languages that we are interested in, which are context-free languages, and then they are going to be equivalent to context-free grammars. Okay, so that's what we are going to study in this unit: how to define formally, mathematically, these push-down automata, how to use them to recognize context-free languages, and how they are equivalent to context-free grammars, which are the tool that we have used so far in order to work with context-free languages. Okay, so that's what we are going to do in this unit, or in this part of the unit. Okay, so let me give you an example of how we can use this new stack, this new storage that we add to the finite automata in order to get push-down automata. When we want to recognize, to accept a language, like for instance this one here, which is the one that we've been talking about, but with A's and B's instead of zeros and ones. So these are words of the form either lambda or AB or AABB or AAABB and so on. Okay, so well, three bits here. So let me write it a little bit more to the left. So this is AAABBB. Okay, so the idea is that, as we have mentioned, we cannot just use the finite set of states that the machine can be into, because we can find an infinite number of situations. So what we are going to do is to use the stack in order to remember how many A's we have read so far. So what we are going to do is to push an A onto the stack every time that we read an A in the string. Okay, so we are reading the tape with the input string, and every time that we read an A, we push a symbol, in this case a capital A, in the stack, and we do this for any A that we read. Okay, and then when we start reading B's, instead of adding more information, more symbols, more elements to the stack, we start popping one of the symbols that we have added on the stack previously. Okay, and if at the end of the word, when we end reading the symbols on the tape, the stack is empty, it means that we have read exactly as many A's as B's, because we have uh, pushed into the stack one A for each A that we have read, and we have popped an A for each B that we have read. And if the stack is empty, it means that the number of A's and the number of B's is exactly the same. If, on the other hand, we stop reading, we finish reading the symbols in the tape, and there are symbols left on the stack, it means that the number of A's was greater than the number of B's. And if we run out of symbols in the stack before we finish reading the, the tape, it means that the number of B's is greater than the number of A's. Okay, so this is the way that we are going to use the stack in this example of this language in order to make the pushdown automaton accept the words of this language. Okay, so let's see how to make this mathematically precise, how to define formally what we understand by a pushdown automaton. And you will notice here that we have 7 elements instead of just 5 in the first unit. When we defined different types of automata, we always had 5 elements. Those 5 elements are still here in the definition of the pushdown automata. So we have a finite set of states, Q. We have an input alphabet. This is what we used to call X, but for some reason in the literature, in the books, it is called sigma instead of X when we talk about pushdown automata, but it's exactly the same as X in first unit. Okay, we also have the transition function, which is a little bit different to the from the transition function that we use with finite automata, but you will see the difference in a minute. We also have, of course, a start state, and we also have a set of accepting states. Okay, so these are the 5 elements that we always have in any of the different types of finite automata that we studied in Unit 1, either deterministic or non-deterministic, or non-deterministic with lambda moves, finite automata. In all of them we had 5 elements, these 5 elements. So again, we have these 5 elements, but now we have some new elements, which are a new alphabet, which is the stack alphabet. Okay, instead of just the input alphabet that is used to write the words in the tape, the words that we want to check. So this is a different alphabet. It can be the same, or it can have some of the symbols in the input alphabet, or completely different ones. It doesn't matter, but it's again a finite non-empty set. Okay, and we also have an initial stack symbol in this definition of pushdown automata. So we have exactly all the elements that we had in finite automata, plus 2 more elements that are what we need in order to define what is in the stack and what happens with the information in the stack. We need an alphabet for the stack and an initial symbol for the stack. Okay, so those are the two additional elements that we need to include in order to define um, pushdown automata. And of course, as always, when we define a new type of automata, um, the main difference is in what the transition function tell us that we need to do when we find some information. Okay, so if you see here, the transition function now depends on three different elements. Okay, let me use this other tool. On three different elements. It depends, of course, on the state the machine is in, and also on the symbol that we are reading on the tape. Okay, so it can be either a symbol in the alphabet of the words of the language that we are studying, or it can be lambda, because we can have lambda moves in this pushdown automata. But these two elements, this q and sigma or x, plus lambda are exactly the two parameters that we had in the transition functions of automata in unit 1. But now we also have a third parameter, which is the information that we have in the stack. So we are going to take into account three different things in order to know what to do in a given at a given moment when we are computing with the pushdown automata. First, we need to take into account the state we are in, then the symbol we are reading in the tape, and then what is at the top of the stack. Okay, so those are the three pieces of information that we need to know in order to determine what the machine is going to do at the next step. Okay, and then this transition function returns two pieces of information. First, the new state that the machine is going to be in, okay? And then what are the symbols that are going to be in the stack? Okay, so these are the new symbols for the stack. So what we do at any given movement of the machine is to read either one symbol from the tape or make a lambda move, and pop one element from the stack, and then change to a new state and replace the symbol that we have popped from the stack with a new set of symbols, with a new string of symbols. This string of symbols can be either empty or non-empty, and in a minute we are going to be what this means. Okay, but for now I want you to understand that we are making moves that depend on a state, an input from the tape, and the element that is at the top of the stack. And we also can make a movement depending on the state of the machine without reading anything from the tape, and always depending on what is at the top of the stack. Okay, and in both cases we are going to have a new state for the machine, and we are going to replace the symbol that we have popped from the stack with a new string of symbols. Okay, this is how the machine works at each given step. Okay, so how does it change? How does the machine change the content of the tape? Is explained in this slide. At each given transition, we change the state, which can be, as in the case of finite automata, exactly the same as the one that we had before. Remember that, for instance, when we had an automaton like this one and we had a loop with A, it means that if we are in Q0 and we read A, we stay in Q0. Here we can also have that for a given state and a given situation with symbols on the tape, symbols on the stack. The machine makes a move, but the new state is the same one as the one that we had before. That is completely possible. It can be different or it can be the same. And we also replace the symbol that is at the top of the stack with a string of symbols from the stack alphabet. And this string can be lambda, can be the same as the symbol that we had before, or it can have multiple symbols. Okay, so the difference is that we always extract the element that is at the top of the stack. We always pop a symbol from the top of the stack. We always do that at any movement of the of the um, of the machine, of the pushdown automaton. And if we replace it with lambda, it means that we have made a pop and we do not introduce anything. Okay, so the number of symbols in the stack is now one less than it was before. We can also replace the symbol with itself, and then it means that the content of the stack does not change. Or we can replace the symbol with multiple symbols, with more than one. In that case, we just pop the element and then we introduce elements again in the stack, and the size of the stack grows. Okay, and of course we can reintroduce the same symbol and new symbols on top of it. So we pop the element, we push back the element on the stack, and then we push new elements on top of that symbol. Okay, we will see examples of those behaviors in different pushdown automata that we are going to work with. Okay, so these are the things that happen when we make a move. We change the state and we replace the top symbol of the stack with either lambda, with nothing, or with just one symbol, or with multiple symbols. Okay, depending on the transition function. Okay, so let's see what happens when we are doing a computation with a pushdown automaton. We always describe the state of a machine with some information that we call the instant description or the instant configuration. And in this case, in addition to the information that we had before, remember that when we were working with finite automata, we always had two pieces of information: the state we were in and the piece of string that we are still that we still need to read. Here, in addition to that, we of course need that information. We also need information about what is stored on the stack. Okay, so we had a new element in the instantaneous description, in the instantaneous configuration, which is this alpha here, which is a string of symbols from the alphabet stack. Okay, and the convention here, in order to read the information in the stack, is that if we have a stack like this, A and B on top of A and C on top of B, then alpha is CBA. So we place the symbol that is at the top at the very beginning of the string, the second symbol after that, the third symbol after that, and so on. Okay, so we read the string from left to right, and this is the top symbol of the stack. Okay, and the other elements are exactly as in the descriptions of finite automata. So we have the current state, the portion of input that is yet unread. Okay, and remember that if it is lambda, it means that we have read all the string already. And we also have alpha now, which is the content of the stack, and it's read from left to right, and it corresponds to the symbols in the stack from top to bottom. And of course, if it is lambda, it means that the stack is empty. Okay, so this is very similar to what we did in Unit 1, but we have a new piece of information, which is the content of the stack, which is read from left to right as if it were a stack from top to bottom. Okay, so with these descriptions, of course, what we always do is to define how to move when the machine is computing, how to change the state of the descriptions of the machine when the machine makes a move. Okay, so in this case, imagine that we have a situation like this one here, in which we are in state Q. We are reading a piece of word which starts with A, and we also have at the top of the stack this A here. Okay, so we need to go to the transition function and see what the transition function tells us that we need to do when we have state Q, when we are reading symbol A, and when we have capital A at the top of the stack. Okay. Also remember that lowercase a here can also be lambda, because we can make lambda moves. Okay. So we check what the transition function tells us for this situation, and it will give us possibly different possibilities, but one of them can be this new state Q prime and this string of symbols gamma. And then what we do is that we replace the new the state of the machine with the new state Q prime. We have read the symbol A. If A is lambda, we have read nothing, but if A is a symbol of the alphabet of the input tape, then we have read that symbol. And notice that we have replaced A with gamma. Okay, if gamma is lambda, it means that we have removed A from the top of the stack. But if gamma has some symbols, it means that we have first extracted A from the top of the stack, we have popped A from the top of the stack, and then we have pushed gamma onto the stack. Okay, and as always, the symbol of the transition of the movement followed by the star means that we are doing one or more transitions at a time. Okay, so this is exactly as the notation that we were using in Unit 1. Okay. Finally, we need to define what it means to accept a word when we are working with pushdown automata. And in this context, we have a slight difference compared to what we had in Unit 1, because we can have two different ways of accepting words. Okay, so the regular way of accepting words, the way in which we accepted words in Unit 1 is what we call acceptance accepts by final state. And in this situation, what we look at is at the configuration that we obtain at the end of the computation when we have read um, the whole word, and it means then that we have lambda as the second parameter in the description because we have read completely the word. And what we need in this situation is that the state that we reach is a final state, is an accepting state. Okay, so this is the usual accepting condition that we used in unit 1, and we can use a pushdown automaton by final states in order to accept a language. Okay, we can do that, but normally we are going to do something that is a little bit different. We are going to use, instead of the state that we reach, we are going to check what is the condition of the stack after we read the last symbol of the word. Okay, so once that we have read all the symbols in the word, in the second parameter of the description, we have lambda. Okay, we have read all the symbols in the word. And what we check then is whether we have completely emptied the stack. Okay, why do we do this instead of checking if the state is final or not, if the state is accepting or not? Because as we have mentioned before, we are going to use the stack as a way of keeping track of whether we have met some condition or not. For instance, in the language that we were using before, these words with exactly the same number of A's and B's, we wanted to have an empty stack. We wanted the stack to be empty because that meant that the number of A's and the number of B's was exactly the same. Okay, so in this case, the most useful indication that we have found a word in the language is not the state, but the situation in the stack. If the stack is empty, then it means that the language is the word is in the language. Okay, so that's why we are introducing this other way of checking whether a word is in the language or not. So when we are using pushdown automaton in order to accept words, we will always say whether we are using it by empty stack or final states. If we are using it by final states, then we need to see whether we are arriving at an accepting state, and if we are using it by empty stack, we need to check whether we are getting an empty stack when we finish reading the word. Okay, and 99% of the time we are going to use this acceptance by empty stack, because as you will see, it's easier to construct the automata thinking about what happens with the stack instead of thinking about what happens with the states. But this is not a restriction, because every automaton that works with empty stack has an equivalent automaton which works with final state, and each automaton that works with final state has an equivalent which works by empty stack. So in some sense they are equivalent. every language that can be accepted with pushdown automata by empty stack can also be accepted probably with a different automaton with final state, and every language that it can be accepted with an automaton by final state can also be accepted by another automaton with empty stack. So we can use the mode that it's better for our goal, and 99% of the time it will be working by empty stack. Okay, so with this concept, then we can define the languages that are um, accepted by automata by either empty stack or final state, and of course the language that is accepted by an automaton, by a pushdown automaton by empty by final state is the set of words in the input alphabet that from the initial configuration in which we have the initial state, the whole word to read, and in the stack we only have the initial symbol of the stack. We always need a symbol in the stack in order to move, because we always pop one symbol from the stack in order to move. So at the beginning we need to have at least one symbol, and we always start with set, which is the initial symbol of the stack. So from this configuration in which everything is initial, the initial state, the initial symbol of the stack, and the whole word, we need to get to a situation in which we reach a final state, an accepting state, and we have read the whole word. This is the set of words that we accept by final state. And if we are working by empty stack, then we again start with the initial configuration, initial state, the whole word to read, and initial symbol in the stack, just the initial symbol in the stack. And in this situation, we don't care which state we reach, but we want the word and the stack to be empty at the same time. So when we finish reading the last symbol of the word, we need the stack to be empty in order to accept the word. These are the two languages that an automaton can accept. Okay? So, uh, to finish today's lecture, let me give you an example of how to make that idea of using the stack to store symbols for A's and then popping the symbols when we read B's, how we can make that idea work in order to accept the words of the form A to the power n, B to the power n. Okay? And of course, the main idea here is that the size of the stack is unbounded. We can use as many symbols in the stack as we want, and this is different to what we have with the finite number of states. There is no bound on the number of symbols that we can use in the word, so we do not have the problem of running out of space and not being able to make a difference between situations with different number of A's. Okay? And in this case, we are going to work by empty stack. So we want the stack to be empty when we finish reading the word, and of course not before, because that would mean that the number of B's is bigger than the number of A's. Okay, remember that the idea is to push A's into the stack and pop A's, push A's into the stack when we read A's, and pop A's from the stack when we read B's. Okay, that's the idea. So what are the elements that we need in order to make this idea formally correct with the definition that we have for finite for pushdown automata. We need 7 different elements. We need first the set of states, and in this case we are going to have 2 different states. State Q0 will be used to read A's, and state Q1 will be used to read B's. Okay, because remember that we have 2 different actions. When we read A's, we push symbols into the stack. When we read B's, we pop symbols from the stack. Okay? Of course, the alphabet in the input tape is AB, because those are the symbols that we use in order to write the words that we are checking. And in this case, the alphabet in the stack, it's going to be a capital A, which is the symbol that we use to count the number of A's that we read, and set 0, which is the initial symbol, okay, in the stack. And Q0 is going to be the initial state. And notice that the set of accepting states is empty, because here we are working by accepting words with empty stacks, so we don't really care about what are the accepting states, because we are not going to check them. Okay, so they can be whatever we want, because we don't care whether we end in an accepting state or not. Okay, so here we have the different transitions that we need with the machine, and notice that we have an initial transition when we have the initial state, the initial symbol in the stack, and we read the first A. When we read the first A, we are still reading A, so we stay in state Q0, and then we push an A into the stack. Notice that we need to write here both the A that we want to push into the stack and the set 0 that we have extracted from the stack. Okay, so initially we have set 0 in the stack, but when we make a move, we always pop the symbol that is at the top of the stack. So we need to pop set 0, and then in order to push the A on top of the set 0, we need to push both A and set 0. Okay, that's why gamma in this situation is A set 0. Okay, the second transition is the one that happens that we are going to use when we have already an A in the stack. We are still in the state in which we are reading A's, and we read another A. So in this situation, in the stack, we will have something like this: set 0, A, another A, probably as many A's as we have read in the stack, another A, for instance. Okay, and then we pop one A, and since we have read another A in the tape, we want to pop an additional A on top of that. So we have these 2 A's that we have not popped. We have popped one A, so in order to increase the number of A's in the stack, we need to pop back the A that to push back the A that we have popped, and to push another A. So that's why here we have AA. Okay, Eventually, we will reach a situation in which we are in Q0, we have read at least one, we have one A on the top of the stack, but now we reach the part in which the word starts having B's, okay? So in this case, we need to change the state to Q1, okay? And we are popping the A, but we are not popping it, pushing it back into the tape, into the stack. Because remember that when we read a B, we want to pop an A out of the stack in order to check whether the number of A's and the number of B's is the same. Okay, so that's why we have lambda here. So we could have something like this. Imagine that we have C0 A. So at this step, what we do is just to pop the A and we replace it with lambda. So it means that at the end we have one A less in the stack. Okay? The next transition is similar, so but now we are in Q1. We have already read at least one B, we read another B, and we have still some A's on the stack, so we do exactly the same. We stay in Q1 and we pop the A. We pop the A and we do not include anything on the stack, so we reduce the number of A's in the stack by 1. Okay? And finally, at some step, we are going to find the initial symbol which is at the bottom of the stack. Okay, so when we remove all the A's in the stack, we are going to find set 0, and when we find set 0, we don't need to use any of the symbols in the tape. In fact, in order to accept the word, there should be no more symbols in the tape, and in that case we just pop the set 0. If at that moment notice that with that action the stack becomes empty. So if at that point we have also read all the symbols in the tape, it means that the number of A's and the number of B's was exactly the same, and then we accept the word because the stack is empty, the tape has been read completely, and that is the condition that we need in order to accept a word when we work by empty stack. Okay. Notice also that there are many transitions that are not written here. For instance, we have not written here what happens with Q1, B, and set 0, for instance. There is no transition for that. So what we mean by writing only these transitions here is that all other transitions are empty. So if we are in a situation in which we have Q1, we are reading a B, and set 0 is sorry, is at the top of the stack, then there are no transitions to make. It means that the machine stops at that moment, and if the stack is non-empty, or if the word is has not been read completely, then the word is not accepted. Okay, so all the transitions that are not explicitly written are empty. Okay, and in that case, the machine does not move. It stops the computation, and if the machine stops, it means that we check whether we have read all the symbols and whether the stack is empty. In that case, we accept, and in other cases, we do not accept. Okay, so let's check what happens with a simple example here with this machine, okay, with the rules that we have written for the machine. Okay, so we are going to check what happens to the word AAABBB, which of course should be accepted because it is in the language, it has the same number of A's and the same number of A's and B's, okay, and all the A's at the beginning, all the B's at the end, okay. So we start with that word with the initial state and only the initial symbol in the stack, okay. So in order to know what is the movement after that, we need to check what's the state, what's the symbol here, what's the symbol here, okay. Notice also that here we could have, instead of a, lambda, okay. So we need to check for transitions of the form qa set 0 or q0 lambda 0. Any of those transitions uh, would give us a possible move for this situation. Okay, in this case, if you check the previous slide, you will see that the only possibility is exactly this transition here. Okay, so that is what we are going to do. We have this transition. Oh, sorry, this transition here that tells us that we should stay in Q0, and we have popped the set 0, but we are going to pop it back, push it back together with A. So the new situation is going to be same state. We have read one of the symbols of the word, and we have pushed the A on top of set 0. So notice that we have popped the set 0 from the stack, and we have replaced it with a set 0. Okay, so for the next movement we need to consider q0, a, and either this a here or lambda. So now we are looking for situations in which we have q0 a or q0 lambda a. And if you check the transitions, the one that we can use is this one here. Okay, in this transition we stay in q0. We have popped here the a, we always pop the a, but we replace this with aa. Okay, so we stay in q0 and we have aa set 0 on the stack. Okay, now we need to look for a similar situation, a situation in which we have exactly one of these possibilities, either q0 aa or q0 lambda a. And of course the only possibility is exactly the same one that we had before, this one, which pops this a here and replace it with aa, also consuming this a here without changing the state. So we now have q0 and aa instead of just one a. Notice that at this moment we have three a's in the stack, because we have read three a's here. We have read three a's here. So every time that we have read an a, we have included another a in the stack. Okay, and now we are in a situation in which we need to look for transitions which are of the form either q0 ba or q0 or q0 lambda a. And the transition that we can use is the one that is q0 ba, which tells us to change into q1 and pop the a without adding anything to the stack. So we pop this a here, we also consume this b here, and we get exactly this situation here with q1 and now an a at the top and a b in the tape. Okay, that is what we are reading in the tape. So now we look for situations in which we have either Q1 um, BA or Q1 lambda A. Those are the possibilities that we can have. And the transition that we can make in that situation is this one here, QBA, which tell us to stay in Q1 and pop the A without adding anything to the to the to the stack. So we consume this B, we pop this A without adding anything, and we get exactly this situation here. Okay, so now we need to look again for Q1 BA or Q lambda A. We are exactly in the same situation. The transition that we can use is this one here, which leads us to Q1 lambda set 0 because we consume this B and we pop this A. And now we are in almost at the end. We have a situation in which the only possibility is to have Q1 lambda and set 0. That is, we can only make a lambda move. But fortunately, we have exactly that kind of transition. That is why we defined the automaton in that way. So now what we do is we stay in Q1 and we remove the set 0 from the stack. And what we get is this configuration here, in which you can see that we have finished reading the word and we have emptied the stack. So the stack is empty. This is exactly what we need in order to accept the word. Okay, so this shows that the automaton works as we want it on this word which belongs to the language. Okay, you can try to do the same with other words in the language, for instance with A, B, B, which should be easier, or with, I don't know, 4 A's and 4 B's. And you can also try to see what happens, for instance, if you have ABB or AAB, and this should not be accepted by the automata. Okay, also if you have, for instance, ABA, this should not be accepted by the automaton. So you can try to do that and see what happens in that situation. So if you have problem finding the behavior of the automaton with those words, please email me or ask me at the virtual meeting that we are going to have on Friday at 11 a.m. Through Microsoft Teams. Okay, so that's all for today's lecture. Hope that it was interesting and that you understood the idea of pushdown automata. See you on Wednesday. Thank you very much.